Hello and welcome to Math World, the world where difficult mathematics can be a very easy one. So today, dear friends, we are going to speak about sequences, and we are going to solve the top 5 hardest exercises in sequences that were presented in different math exams. So be ready to see how to solve the top 5 hardest exercise. So let's start with the first exercise, which states that we have the three terms of a quadratic sequence un equals to an squared plus bn plus c. So the first two terms are 1, 3, and 7. And we have to find an expression in terms of n for the nth term of this quadratic sequence, and to find n for which un is equal to 111. So first I will start with the idea how to find the general formula for this quadratic sequence. So we had that the general formula is un equals to an squared plus bn plus c. And also we have that the first term u1 is equal to 1, u2 is equal to 3, and u3 is equal to 7. If we have the information about the first three terms, we will use this information and we will find the first two terms according to our formula. So according to our formula, from this formula, we have that the first term, u1, will have the form a multiplied by 1 squared plus b multiplied with 1 plus c, which in fact gives us a plus b plus c. And from the condition, we have that a plus b plus c should be 1 because the first term of our sequence is 1. Next, from this formula, we have that u2 is equal to a 2 squared plus b2 plus c, which in fact is 4a plus 2b plus c. So we get that 4a plus 2b plus c must be equal to 3, because the second term of our sequence is 3. Next, we are going with the third term, u3 is equal to a multiplied by 3 squared plus b multiplied by 3 plus c, which in fact is 9a plus 3b plus c. And we get that 9a plus 3b plus c must be equal to 7, because the third term of our sequence is 7. And now, for finding the values of a, b, c, we have to solve this system of three equations in three unknowns. A plus b plus c is equal to 1, 4a plus 2b plus c is equal to 3, and 9a plus 3b plus c is equal to 7. So we have a system of simultaneous equations. So how we are going to solve? We are going to do the following small trick, because all the three equations have the last term c with the same coefficient 1. I'm going to subtract from the second equation the first equation, and we will get 4a minus a, 3a, 2b minus b will be plus b, c is reduced, 3 minus 1 is equal to 2, and if we subtract from the third equation the first equation, so we'll get 9a minus a, 8a, 3b minus b plus 2b is equal to 7 minus 1, it will be equal to 6. Now, the second equation, we can divide both sides by 2, and we get the following, that 3a plus b is equal to 2, and 4a plus b is equal to 3. Because we have the same coefficient b in the both equations, we can subtract from the second equation the first equation, and we will get 4b minus 3b a, 4a minus 3a is equal to 3 minus 2 is equal to 1. So we found that a is equal to 1. Next, we are going back in the second equation from the last system, and we are going to replace, instead of a, the value 1. and we will get that 3 multiplied by 1 plus b is equal to 2, from which we get that b is equal to minus 1. And next, for finding the value of c, we are going to replace a with 1 and b with minus 1 in one of the equation that you like from the first system of equations. So I'm going in the first equation. So here, instead of a, I'll put the value 1, and instead of b, the value minus 1. So we will get that 1 minus 1 plus c is equal to 1, from which we will get that c is equal to 1. And so we had that our general term of the sequence un has the following formula. A is equal to 1, b is equal to minus 1, c is equal to 1. It gives us n squared minus n plus 1. And so easily we solved the first part of our exercise. Next, we can move to the second part of our exercise. We had that un is equal to 111. And now, because we have the general formula, we get that n squared minus n plus 1 must be equal to 111, or n squared minus n must be equal to 110. We get a second order equation. We can solve this equation using the general form, but this equation can be solved using a small trick, because we are solving in positive integers, and the left side of this equation can be factorized in the form n multiplied by n minus 1 is equal to, and 100 is equal to 110. And we can see that here in the left side we have the product of two consecutive numbers, because n minus 1 and n are consecutive numbers. So we have to find two consecutive numbers which multiplied will give us the value of 110. And for sure it is 10 and multiplied by 11. So from this we get that n is equal to 11. So the solution to our exercise is the following, that un is equal to n squared minus n plus 1, and n is equal to 11 in such a way that un is equal to 111. So the 11th term of our sequence is 111. So let's move next to the second exercise. And we have the following, that if the sequence un is equal to n plus 1 multiplied by 5 to power n, we have to show that un plus 2 minus 10 multiplied to un plus 1 plus 25 un is equal to 0. So the idea in this exercise first is to deduce the formula for un plus 1 and the formula for un plus 2 if we have that un is equal to n plus 1 multiplied by 5 to power n. So first let's start with formula for un plus 1. This means that we are going to the general formula, and instead of n we are going to put n plus 1. So instead of this n, we'll replace n plus 1. This means that instead of this n, we are replacing n with n plus 1, and here also with n plus 1. So the formula for un plus 1 will be n plus 1 and plus 1 from exercise multiplied with 5 to power n plus 1, which in fact gives us that un plus 1 has the formula n plus 2 multiplied to 5 to power n plus 1. So I'll write here that un plus 1 is n plus 2 multiplied to 5 to power n plus 1. Next, using the same idea, we'll deduce the formula for un plus 2. This means that we are going here in the general formula, and instead of n, we are going now to put n plus 2. So here we'll put n plus 2, here n plus 2, and n plus 2. And we'll have the following: n plus 2 n plus 1 multiplied to 5 to power n plus 2, which in fact gives us n plus 3 multiplied to 5 to power n plus 2. So un plus 3 is equal to n plus 3 multiplied to 5 to power n plus 2. Next, we are going to our expression that we have to show that un plus 2 minus 10 un plus 2 minus 10 un plus 1 and plus 25 un is equal to 0. So we have to show this equality. What we are going to do? Very simple. We are going to replace un plus 2 with its formula that we obtained n plus 3 multiplied by 5 to power n plus 2. Next, minus 10, and un plus 1 we are going to replace with its formula n plus 2 multiplied to 5 to power n plus 1. Next, plus 25 multiplied to, and un we are going to replace with general formula n plus 1 multiplied to 5 to power n. And we have to show that all this expression is equal to 0. Next, I will remember you some properties from the powers, and we have such property that a to power n multiplied with a to power m is equal to a to power n plus m. And we can read this property from right to left. It states that a to power n plus m is equal to a to power n multiplied to a to power m. So this is a very important property that we have to use here. So I will use this property for 5 to power n plus 2 and for 5 to power n plus 1. And we will get the following: n plus 3 multiplied to 5 to n multiplied to 5 to power 2 minus 10 n plus 2 5 to n 5 to 1 plus 25 n plus 1 5 to n is equal to 0. Next, what we have to do is to analyze this expression, and we can see that all three terms contains 5 to power n, and we can subtract this common factor 5 to power n from all the terms, and we will get the following: n plus 3 multiplied to 5 to power 2, which is 25, minus 10 n plus 2 n multiplied by 5 plus 25 n plus 1, which we have to show that is equal to 0. Now let's do the calculations from this parenthesis. So we'll get 5n multiplied. If we open the brakes, we'll have 25n plus 75 minus 10 multiplied by 5 is 50, so we'll have 50n minus 100. Sorry, here is 75, not 70, sorry. 75. So, and the last bracket will give us 25n plus 25. We have to show that this is 0. And in reality, 25n plus 25n minus 50n is 0. 75 plus 25 minus 100 is 0. So we get 5 to n multiplied by 0, which in fact is 0. So we showed that that expression is equal to 0. And this was the second exercise. Let's move next to the third exercise. And the exercise states the following. If un is equal to 4 multiplied with n plus 1 factorial, show that un plus 1 minus n multiplied by un is equal to 2un. So the idea is the same as in the previous exercise, because we have here un plus 1. From the formula of un, we will deduce the formula for un plus 1. This means that instead of n, we will put n plus 1, and here instead of n, we will put n plus 1. And we get that un plus 1 is equal to 4 multiplied by n plus 1, n plus 1 factorial, which in fact gives us 4 n plus 2 factorial. If you forget what does factorial means, we say that m factorial is 1 multiplied by 2 by 3 and so on till m. So this is the definition of the factorial for a positive integer. Now let's replace our expression un plus 1 minus n un equal to 2un with the expression. So instead of un plus 1, we will put the expression 4 multiplied by n plus 2 factorial minus n. Instead of un, we'll put its formula 4 n plus 1 factorial. We have to prove that this gives us 2, and instead of un, we'll put 4 n plus 1 factorial. Next, a small trick what we have to use is the following, that we just have to see that n plus 2 factorial, by definition, it is 1 multiplied with 2, with 3, and so on, multiplied by n plus 1, and multiplied with n plus 2. But if we analyze 1 multiplied by 2, by 3, by 4, and so till n plus 1, it is nothing else as n plus 1 factorial. So n plus 2 factorial is equal to n plus 1 factorial multiplied to n plus 2. So instead of n plus 2 factorial, replacing with the expression that we obtained, we have 4 n plus 1 factorial multiplied to n plus 2 minus 4n multiplied to n plus 1 factorial. We have to show that this gives us 8 n plus 1 factorial. Next, from the left side, we can see that we can take some common factors. 4n plus 1, and here we also have 4n plus 1. So subtracting 4n plus 1 factorial as a common factor, we'll get that it remains n plus 2 minus n. And we have to show that this is 8 n plus 1 factorial. Plus 1 minus 1 gives us 0. So we obtain that 4 n plus 1 factorial multiplied by 2. We have to prove that this is 8 n plus 1 factorial, which is for sure true, that because 4 multiplied by 2 is 8, so 8 n plus 1 factorial is equal to 8 n plus 1 factorial. And we proved our condition. So this was the third exercise that I wanted to show you. Now let's move next to exercise number 4, which states the following, that if un is equal to n plus 3 over the 2n plus 1, show that this sequence is a monotonic decreasing one. Let's remember what does a monotonic decreasing sequence mean. So if the sequence un is a monotonic decreasing, so it decreases, I draw like this. This means that un plus 1 is less than un for all n belonging to positive integers. So, in fact, we have to show that for all positive integers, un plus 1 is less than un. So, for proving this, of course, we have to find the formula for un plus 1. As in the previous examples, we just have to replace this n, this n, this n by n plus 1 in order to get the formula for un plus 1, and we will obtain n plus 1 plus 3 over the 2 multiplied with n plus 1, which in fact will give us n plus 4 over 2n plus 3. So next we have to prove that n plus 4 over 2n plus 3 is always less than n plus 3 over the 2n plus 1. How are we going to prove this? Because n is a positive integer, for sure 2n plus 1 is more than 0, and 2n plus 3 is more than 0. So this means that the product 2n plus 1 and 2n plus 3 is more than 0. So we can multiply this relation with 2n plus 1, 2n plus 3. And we are sure that this sign will remain unchanged because we are multiplying with a positive expression. When multiplying both sides with 2n plus 1, 2n plus 3, we will get the following. So we will get that n plus 4, we have to show that n plus 4 multiplied with 2n plus 1 is less than n plus 3 multiplied with 2n plus 3. Now we are going to open the brackets and we will have 2n squared plus n and 18 plus 9n and plus 4. We have to show that it is less than 2n squared plus 3n plus 6n, 9n and plus 9. Which in fact we have, because here is 2n squared on both sides, 9n, 9n on the both sides. So in fact it gives us to prove that 4 is less than 9, which is true for all n belonging to positive integers. This means that un plus 1 is always less than un, and this means that un is a monotonic decreasing sequence. So this was the exercise number 4, and next let's move to exercise number 5. So in exercise number 5 we have the series Sn equals to u1 plus u2 plus u3 plus so on un, where Sn is equal to 2 to power n plus 1 plus n squared. And we are asked to find an expression for un, to evaluate u5, and to show that un plus 1 minus 2un plus 2n is a constant. So let's start with point A. For finding an expression for un, you have to know that. How to find this expression if you have the series Sn u equals to u1 plus u2 plus so on plus un. What you have to observe is that if you calculate Sn minus 1, which in fact is u1 plus u2 plus so on till un minus 1, and if you subtract from Sn minus 1, which in fact from u1 plus u2 plus so on plus un, you subtract u1 plus u2 plus so on plus un minus 1, it will give you un, because u1 minus u1 will be 0, u2 minus u2 will be 0, and so on. Un minus 1 minus un minus 1 will be 0, so it remains un. So un, we prove that it is equal to Sn minus Sn minus 1. Now, what we are going to do, we are going to find the formula for Sn minus 1, having that Sn is equal to n plus 2 to power n plus 1 plus n squared. And the idea is the following. For finding S minus 1, we have to replace n with n minus 1, and this one to replace with n minus 1, and this n to replace with n minus 1. So, in fact, will give us Sn is equal to 2 to power n plus 1 plus n squared minus, and Sn minus 1 is 2 to power n minus 1 plus 1 plus n minus 1 squared. And we have 2 to power n plus 1 plus n squared minus 2 to power n plus n squared plus 1 minus 2n. So opening the brackets, we'll get 2 to power n plus 1 plus n squared minus 2 to power n minus n squared minus 1 plus 2n. Now, 2 to power n plus 1, we'll write it as 2 to power 1 multiplied with 2 to power n. So 2 multiplied with 2 to power n plus n squared minus n squared is 0. Next is minus 2 to power n minus 1 plus 2n. And 2 multiplied with 2 to power n minus 2 to power n, in fact it is 2 to power n. So we'll get 2 to power n minus 1 plus 2n. So we obtain that un is equal to 2 to power n minus 1 plus 2n. So we solve point A. Next, point B. Evaluate u5. Because we had the formula for un, u5 will be 2 to power 5 minus 1 plus 2 multiplied by 5. It will give us 32 minus 1 plus 10, which is 41. Next, point C. We have to show that un plus 1 minus 2 un plus 2n is a constant. It means that we have to prove that this expression does not depend on n. For this, we have to find first the formula for un plus 1. To find this, we have to go back to un and to replace this n, and this n with n plus 1. And we will get that un plus 1 is equal to 2 to power n plus 1 minus 1 plus 2 n plus 1, which is 2n plus 1 minus 1 plus 2n plus 2. This equals to 2n plus 1 plus 2n plus 1. And we can back here and to replace un plus 1 and un with their formulas, and we'll get 2n plus 1 plus 2n plus 1 minus 2 multiplied to 2n minus 1 plus 2n and plus 2n, which will give us 2 to power n plus 1 plus 2n plus 1. Now, opening the brakes, we will have minus 2 to power 1 multiplied to 2 to power n will give us 2 to power n plus 1 plus 2 minus 4n plus 2n. Now, 2 to power n plus 1 minus 2 to power n plus 1 is 0. 2n plus 2n minus 4n is 0. And plus 1 plus 2 is 3, which is a constant. And we prove that that expression is a constant, the thing that we had to prove. And so we solved the exercise number 5. So dear friends, these were the top 5, the hardest exercise from exam papers which contain sequences. Thank you very much for your attention, and please like this video, share this video with your friends, and subscribe to our channel Math World, the world where difficult mathematics is a very easy one. Thank you and goodbye.